In this module, we'll connect cryptography to real architectural decisions. You'll see how a few basic primitives let us prove three things about identity data and audits: that the content wasn't changed, who produced it, and how it evolved over time. Cryptographic hashes are like data fingerprints. You feed in any amount of information, an eKYC dossier, a log line, a PDF, and get a fixed size output. That output reveals nothing about the original data, but even a 1-bit change produces a completely different fingerprint. This avalanche effect makes hashes ideal for tamper detection and for building verifiable audit trails in identity systems. Hashes show up in identity systems in three practical ways. For document storage, you hash the document and store the hash alongside, or instead of the raw file. Later, you can prove nothing changed by recomputing and comparing that hash. For API transmission, you hash or HMAC the payload, send both, and verify on receipt to detect tampering in transit. For privacy-preserving checks, two parties compare hashes instead of raw identifiers, enabling matching without full data sharing. Hash-chained audit logs treat every important action as a block: upload, verification, approval, and so on. Each block stores a hash of its own contents plus the hash of the previous block. That simple trick gives you three things: a mathematically provable ordering of events, immediate detection of any historical change, and a clear chain of custody. If an attacker alters an old record, its hash changes and breaks the chain, so you can prove exactly which version is authentic. Choosing a hash algorithm is really choosing how long your integrity guarantees should remain believable. MD5 is completely broken for collisions, and SHA1 is effectively broken. Treat both as high risk and never use them for new identity or audit data. For current systems, SHA256 or SHA-384 are the practical baseline. If you need very long-term integrity or are designing high-assurance trust anchors, start planning around SH3 variants and be ready to rotate as standards evolve. Digital signatures let you prove three things about a KYC result or any decision artifact: who produced it, that it hasn't been altered, and that the signer can't later deny issuing it. The issuer signs with a private key that must stay tightly controlled. Anyone holding the matching public key can verify the signature without learning the private key. Architecturally, this turns every KYC decision into a cryptographically bound statement, anchored to a specific system or legal entity. In practice, we're turning messy, mutable data into signed, auditable facts. First, the identity provider takes raw user data, runs its checks, and then signs an identity assertion with its private key. Anyone with the public key can later verify who issued it, what was asserted, and until when it's valid. Separately, the compliance stack signs the KYC outcome. That gives you two independent, cryptographically sealed claims: who this is and what due diligence decision we made, when. You can think of a signed decision artifact as a small, self-contained evidence package. At the top, you declare how it will be verified: which key, which algorithm. In the middle, you capture the full decision context: risk scores, rules fired, hashes of all inputs, and a precise timestamp. At the bottom, you apply a digital signature over both header and payload. If any bit changes, verification fails, and auditors can reliably reconstruct exactly what the system decided and why. Key management is lifecycle management for secrets. You create keys in a controlled environment, then activate them only when governance conditions are met. During usage, enforce RBAC so only specific services can call cryptographic operations, and never export raw keys. Rotate keys regularly to limit blast radius and satisfy compliance. Retire keys once they're no longer needed for new operations, but keep wrapped copies for legacy decryption. Finally, securely destroy keys when retention windows expire, so old data can't be silently resurrected. Hardware security modules and cloud KMS act as your trust anchors. The core idea is simple: keys live and die inside a hardened appliance and never cross the boundary. Your applications send data or hashes over an API. The HSM performs encryption or signing internally, and only the result comes back. Because keys are never exported, you get strong resistance to key theft plus tamper-evident, crypto-level audit logs that regulators and security teams can rely on. PKE becomes the trust backbone for your identity and KYC decisions. At the top, you have a root certificate authority, which everyone agrees to trust. That root issues certificates to intermediate CAs, and those in turn issue certificates to services like your identity provider. When a client verifies a signature, it walks this certificate chain upward. If every link validates and ends at a known root, the signature is accepted. So managing roots and intermediates correctly is critical to your overall trust architecture. Choosing a trust model is really choosing who you're willing to depend on and how much coordination you can afford. Centralized models give you tight control and simple governance, but they lock you into a single root and make interoperability hard. Federated models spread trust across a few institutions, which improves interoperability, but requires legal frameworks and shared policies. Decentralized and SSI models maximize interoperability and user control, but demand the heaviest governance and standards work. Now we chain together everything we've built into a single verifiable pipeline. A user action starts the flow, but from that moment on, every transformation becomes evidence. Data is hashed, so integrity is locked in. Then the risk engine produces a decision that's immediately wrapped by an HSM-protected key. That signed decision is committed into a hash-chained log, turning a point-in-time choice into a durable cryptographic fact that regulators or counterparties can independently verify later. As you move toward implementation, treat cryptography as something you'll replace, not something you'll finish. Design clear abstraction layers so you can migrate hashes, ciphers, and signature schemes with configuration changes, not rewrites. Feed every sensitive crypto event into your security monitoring pipeline, so anomalous key use becomes an alert, not a forensic surprise. And enforce operational discipline. Automated key rotation, regular recovery drills, and periodic verification that every trust anchor is still trustworthy.